Oh, but Raymond, oh, okay, yeah, the recording. Yeah, sorry, you go.
Yes.
Yeah.
Thank you, sir. Yes, we were saying today that the first sentence of the speaker is always "this meeting is being recorded." All right, no, but thank you. Thank you very much for the invitation. So I'm going to cover a bit the story of the neutrino option, more from the origin, and then in the final part of the talk, if I have time, I will discuss a bit the question of UV completions that concerns a bit more recent papers also by other authors, and all the part that is my work was in collaboration with all these people here. So Mike Trott, with which we had the original idea, and Christian Moffat, Silvia Pascoli, Sergei Petkov, and Jessica Turner for the part of leptogenesis, and Jim Tolbert for a part of UV completions that I'll mention at the end. All right, so even though this is a neutrino kind of topic, it's actually starting from a hierarchy problem, which I think you're very familiar with. So the fact that the Higgs doesn't have a dynamical origin in the scalar potential leads to a lot of theoretical problems. So I personally come from the point of view of effective field theories. That's kind of my expertise. So the way we formulate this in an effective field theory framework, just to set the language, is that you typically have, so if you have, I mean, in physics that can couple to the Higgs boson, so like a generic vector or a scalar or a fermion, like in this case, when you do the EFT operation of integrating out the heavy particle, this will lead to non-vanishing threshold matching contributions. So basically a non-zero remnant that does not disappear when you send the mass to infinity, and that comes from these sorts of diagrams. And consistently with the trivial expectations, these threshold contributions are going to be proportional to the mass of the heavy particle itself, which is the hierarchy problem, and this is how it comes up in this context. So the traditional solutions in this sense are either trying to force cancellations between the thresholds, so this is what you would like to do in a supersymmetry way, or to suppress them. And for instance, in composite Higgs, one basically says, let's say that the Higgs has a shift symmetry because it's a Goldstone boson, so this somehow makes it natural to have a suppression factor to these contributions, so you generate the potential radiatively and so on and so forth. The difficulties, yes.
Why are you calling the supersymmetry cancellation among thresholds?
Well,
I mean,
when
it cancels way above the thresholds as well, right? I mean,
yes,
it kind of doesn't matter what it's quite the reverse. It doesn't matter what my thresholds are. It all cancels, right? I mean, like if I push the thresholds very high, then it's a problem. But otherwise, it cancels regardless of the thresholds.
Yes, I'm not sure we're disagreeing. So what I meant is that, so like in the limit in which you impose exact supersymmetry, then of course there are all the other factors. You're requiring like the scalar to cancel with the fermion component to be exactly equal. So you impose a symmetry such that they cancel off.
No, but the important part is that everything above the threshold cancels because there is a log sensitivity. There's only a log sensitivity to any UV cutoff. Right?
Also, yes, sure. Sure,
that is more relevant for the gauge hierarchy problem than the cancellation of the thresholds. So who cares what the top mass and the stop mass is? It's important part that when they have, I don't know, 10 to the 10 GeV virtual contributions, they cancel exactly, right? That's
yes, sure.
That's the point.
Yes, no, you're right. Yes, I agree. I was thinking of the threshold, but I agree. Yes. So I was saying, yeah, so the usual troubles is that all these models, one way or another, they require resonances that cannot be too far from the rhetoric scale because the stabilization and the generation itself for the scalar potential is close to the TV scale, and that all the potential must be generated at once, which is a non-trivial operation. So one, even for the composite Higgs, needs to have a tuning of parameters in order to have all the experimental constraints to be satisfied, essentially, which leads to this very baroque spectrum and the symmetry setups with fermions and so on. So originally, when we were thinking of this idea of the Neutrino option, the way it came up was that, well, okay, now that we have the Higgs mass, of course, you have all these studies that have to do with with the RG running of the scalar potential. So this gives you the opportunity to control the dependence of the parameters as a function of the scale. So you don't really have to put the stabilization problem close to the electroweak scale or to the TV, but you could in principle move it somewhere else and then connect the two points. So connect down to the electroweak scale by running. So schematically, the general idea, which does not necessarily apply only to the neutrinos, but it's kind of the perspective point of view, is that you have the running of the lambda coupling that is referring to this axis. These are two independent plots on top of each other. And the running of the Higgs mass that maps to this right axis here. You have the TV, which is usually where you work when you do BSM models trying to answer to the hierarchy problems, but you could also work, for instance, closer to a lambda gets closer to 0, for instance, because, I don't know, maybe it's easier to generate the potential there. So you have some sort of new physics that decouples at a very high scale. So you have that the initial conditions are set by the thresholds at this point, and then they run down essentially with the standard model RGE, because you assume that below this scale you have no other particle except the standard model ones. So this is, in a nutshell, the game that we played with the type 1 seesaw. We chose the type 1 seesaw because it's just the most trivial extension of the standard model, which I think is very compelling as well. This slide is just here to set the notation and to say that I'm going to use omega for the Yukawa, which is a funny thing, but just that's the notation that we used. So when you take the type 1 seesaw and you do the FT thing of integrating out the heavy retandem neutrino, you have a level component to the matching, which is the usual thing that goes to neutrino masses, so to the Weinberg operator. And then at one loop, you have a matching contribution to the Higgs mass. This equal should not be there, scales like the mass squared of the heavy neutrino, and then it's suppressed by 2 powers of the Yukawa. And then you have a threshold contribution to the quartic that does not depend on the mass, depends only on the Yukawa coupling, because you don't need any chirality violation. These are results that were read in the literature. We just recheck them and rewrite them independently. So you have essentially 2 free quantities, which is the scale of the heavy mass and the size of the Yukawa coupling. Then you can also consider flavor indices. I'm gonna talk about that later. But in first approximation, if you assume no tunings, you have 2 relevant quantities. And you see that you have essentially 3 constraints, because you need to fix both parameters of the Higgs potential and also to have neutrino masses that are consistent with what is observed. So the trivial question that we asked to begin with was, is it possible to have something that satisfies all these? So the preliminary analysis in the first paper was that we decided to focus first on the Higgs potential. So fix the 2 free parameters in order to generate the correct Higgs mass and the quartic coupling, and then check if this was consistent with the neutrino masses. And in doing this, we assumed that all the scalar potential was generated by the heavy neutrino. So that we basically started with a classical potential that was nearly vanishing. So with an approximate scale invariance, but also on top of that with an approximately vanishing quartic coupling, which is a bit of a too strong assumption, and I will get back to this again. But this is where we started from, like full ambitious setup.
Does this correspond to any additional enhanced symmetry or not? No.
No, in fact, then it can be removed. I mean, the shift symmetry, if you want. If you wanted it to be completely shift invariant for the Higgs, you recovered like the Goldstone boson nature, then you can probably do it, but not really.
But
like the quartic coupling is.
Yukawas are not shift symmetric. So
exactly. So yeah, you have to break it to some extent. You cannot really keep it. So I will relax it later. I mean, this doesn't really rely on that in the end of the day.
So you'll also talk about the Planck scale, how it breaks scale invariance, and how that will, and the assumptions that you made about that as well later.
Not really. So I can mention it when we talk about the UV completion. So the neutrino option idea has a finite validity range, and it does have this weakness of saying I want something that starts nearly conformal invariance, but for instance, I do have the Majorana mass.
Yeah.
That's a scale.
Yeah.
So it has an attractive side, which is you have one parameter that controls scale invariance and lepton number violations, for instance, which could be an interesting identification, but it does need a UV completion. This is not a solution. It's not a UV complete model. But there are papers that address this question by
so you said that you're not going to give a UV completion later. That's what you said. Is that
I'm
right?
going to talk about possible UV completions that have been suggested,
okay.
But since it's not mainly my work, then
yeah,
I can refer you to the papers that I will do.
Okay, yeah, great. Thanks.
All right, so in doing this operation, essentially we found that lambda is not very sensitive to omega in the sense that the Yukawa needs to have such a small value that when it's to the fourth power, whatever you get is always basically 0 as the size of the threshold matching contribution. So if you wanted to match lambda with, so such that when you fix it at the threshold scale, then you run it down with the RG equations and you get the measured value. Basically, the point where you have to set the matching scale is at 10 to the 7 GeV. And then once you have fixed this, you can go and look by varying the Yukawa coupling if you get the correct Higgs mass. So in this case, this is the line that you have having fixed the mass at 10 to the 7 GeV. And in order to cross with the measured value, you find that you need a Yukawa that is about 10 to the minus 4.5, something like this. And at this point, you have everything fixed, and you can check what you get for the neutrino masses. And we were very positively surprised at the beginning to see that the value for the sum of the neutrino masses, we didn't take into account flavor, so we just multiply by 3, was about 10 to the minus 3 electron volt, which is in a very nice ballpark. The thing is that here there are a lot of buried bodies, so this is not really the super refined solution that you can get. So the main effect that I cheated about was the numerical, or cheated about, this was the preliminary analysis, let's say, but to refine it, you need to consider, for instance, the numerical sensitivity to the size of the top mass in the running loop, and at which order you compute the RG. So the numbers that I just showed were derived with 1 loop RGs in the standard model, but if from 1 loop you go down to 2 loops, you see that already your preferred values shift towards higher masses and lower Yukawa couplings, which means 2 small neutrino masses. So size of neutrino masses that are below the mass splittings that we're observing. So even having the lightest as massless, this value is way too small. And then it also had the 2 unattractive features that, okay, this basically remain the fact that you cannot have thermal leptogenesis.
If you abandon this lambda equals to 0 in the UV assumption,
yes.
You probably can rectify it, no?
Yes, that's what we did.
In some sense.
Yes, so we changed the analysis. And you basically relax this. But then you have 3 parameters and 3 constraints, so you have to decide where to start from. So we did it better, and we decided to fix the neutrino masses and the Higgs mass, and then see what we get for lambda, because lambda doesn't really have any constraint, as you say. I mean, it doesn't have any theory constraint, and okay, you measure it and fine. And in doing this, since we were improving the analysis, we also added the flavor effects. So what we did was that we fixed it. So in fixing the neutrino masses, we actually fixed all the mass and mixing parameters at low energy via the Casasibara parameterization, and then we ran it up consistently. So when you change this operation, you actually find something nice, which is since neither the neutrino mass nor the Higgs mass vary much with the running. So if you run them, they remain more or less in the same ballpark. They don't change orders of magnitude like lambda. Basically, you can identify just by imposing these 2 constraints the size of the Yukawa and an upper limit for the heavy mass in a way that is very stable and doesn't depend really on how you're doing the calculation, if it's 1 loop, 2 loop, 3 loops, if your top mass varies or not. And we should have realized this earlier, but this is actually also a nice thing. And so this is basically the identification of what you need to have for the neutrino option, and it's very hard to move from this value. So still at the ballpark that we identified in the previous analysis still respected. So I was saying 10 to the 7 GeV, which is 10 to the 4 TeV. It's again the same range that we identified with the previous analysis. And then the Yukawa has to be roughly 1/m in units of TeV. So this is again 10 to the -4. You don't go too far. So the first guess was also quite correct. So the plot here is basically just showing the value of the Higgs mass. The red line is the value that you run up from the standard model, and you see that in this scale is basically constant. And the bands are the value that you get from the expression of the threshold contribution using the numerical values that correspond to the neutrino masses run up. So you fix all the Yukawas from the neutrino masses and mixings, you run them up. So because they have an uncertainty, this is a band. And as a function of the mass at the denominator, this is the band that you get. So what you want is that the two lines cross so that the threshold contribution is equal to the value that you actually want to have from running up. So we tried this for these two different scenarios. So when the heavy neutrinos are fully degenerate, and this is the maximum value that you have. And then if you have that one neutrino is 10 times heavier than the other, just as a benchmark, you end up down here for the value of the lightest mass. So basically, this is saying that the only mass that matters is the mass of the heaviest, right, and the neutrino. So if I put the heaviest, sorry, if this is the mass of the lightest, so if the heaviest is 10 times heavier than this, you end up back here, basically again. So this is just the value of the heaviest, and it has to be around 10 to the 7. What happens with lambda now? So we have fixed all the Yukawas and the masses. So now we can do the same again with lambda. So this shows the value of lambda that runs down from the standard model value with 1, 2, and 3 loop RG. So reverse these 1, 2, and 3. And these are the bands, the dotted points where you cross the correct value for the Higgs mass. So you want your threshold, if you generate the potential purely like this, to cross the red line within this band, which clearly doesn't happen because the threshold for the lambda, as I said before, is basically 0. So this is again the same plot, but in log scale for positive and negative values. And you see here that the threshold corrections, if you want to match the neutrino masses correctly, the threshold correction is always 10 to the minus very high power.
What's NRG?
It's how many loops you use to calculate the standard model RG. Mm-hmm. And this depends significantly. I mean, from 1 to 3 loops, you push this thing away from like 3-4 orders of magnitude. So that's a very sensitive effect. So, well, the conclusion is that you do need to start off with some sort of bare value of lambda, but the good news is that it's in the perturbative range because lambda basically is only the bare value that it had at the beginning.
Sorry, could I ask a question? I mean, normally when you have to break electroweak symmetry, so the Higgs mass has to run negative. And typically for SUSY and composite Higgs, it's the top contribution with a large Yukawa coupling that switches the sign from positive to negative. So how does it work in your model with this neutrino option? Because the Yukawa coupling is really small, so I don't see how you overcome the gauge contribution.
So it's actually, we're actually leaving it as in the standard model. So the way we're doing it is that we're decoupling the heavy neutrino at its mass. And then below that scale, you only have standard model particles. So the idea is that basically it happens just in the same way as in the standard model.
Tony, the Yukawa, you're right, is small, but the mass is huge, right? The mass is much larger than the electroweak scale. So you get whatever Yukawa squared times the quadratic contribution of the mass squared, right? That's
yes, and it's still a fermion, so it's still same sign.
Yeah. So basically, you're starting. But is the initial condition that you're starting with 0 Higgs mass and then it immediately runs negative? That's basically what that's what's happening here.
Well, yes, it starts off directly negative. It depends on if you're thinking, so the value that I'm writing here is the physical mass, but then the Lagrangian would be the minus this thing. So it starts off negative and already at the right value. because the loop is the loop of fermions, so it's negative.
I see.
It has exactly the same sign. I mean, the one important point is that you can only play this game with fermions or with a net contribution that is fermion-like, because you need to have the right sign. Otherwise, it doesn't run the way you want it.
So the braking is put in automatically then,
Yeah.
as opposed to
Yes,
radiating.
yes.
Tony's
It's implicit in the
thinking about
calculation.
radiating.
Yes. I mean, if you want to have something where you generate a mass positive and then it runs negative, you have to go to very high values, because then you rely only on the standard model RGE. So you have to go where at the scales where the standard model starts being unstable, right? In order if you want to have the phase transition happening there without anything else.
So then you are putting in a negative at the beginning, right? Is that what you're saying?
Yes, it starts off
Oh,
negative and then you put it directly at the right value, and then it basically stays constant. So like you generate it here and then it follows the red line, and that's the Higgs mass.
Yeah, I see. But then that's a bit different than SUSY and composite Higgs, right? Which gives you a reason for why you break electroweak symmetry then, right?
Yes, it is. I mean, again, this is not a full answer, but it's a possible mechanism with which you could kick it in. You just need to have some negative loop of some sort, and then you have to justify why you have no other contribution that compensates for it. So you have to start from something conformal or but nothing else that destabilizes this process.
Yeah, I see. Okay, thanks. Yep.
Well, it can be used as like a motivation of the scale 10 to the 4 GeV, right? In some sense.
Yes.
That's what we derive out of this.
Yes, essentially. Yes.
Sorry, I have a question on slide 12. The slide before this one. Yeah, so the effect of the 3-loop rounding seems to be even larger than the effect of the 2-loop. So still you're worried that higher loops become even more and more important?
Yes. I mean, okay, I'm not an expert in the loop calculation for the standard model RGE, but I think this is not a great sign, but this is really how it goes. Then I cannot tell you if maybe there is something that enters at 3 loops that does not enter at 4 loops. I don't know. I don't know if anyone has looked into it. But yeah, I agree that this is a bit worrisome. But this is what like all the vacuum stability studies were based on. Maybe they have some comments on this. I can check that paper.
Yes, thanks.
Okay, so this is just a summary of the values that we find depending on all the parameters that we may vary. So if we use the 3 loops RGE, the mass of the lightest guy sits in between 10 to the 6, 10 to the 7 GeV. And this is how it varies, varying basically the value that we take for the top mass between 171 here and 175 there. The 2 dots are normal or inverted hierarchy for the neutrinos. And the 2 colors are if they're degenerate or if one is 10 times heavier than the other. And the point here is the one that we found essentially for the very first analysis. So we were using the 1 loop RG. We thought, okay, being very naive, does everything match? And we found that we could have a vanishing lambda nearly as well at roughly the same mass. But then if you use the proper RG, this gets shifted up and up. Not an issue because again, it's really in the perturbative range, so it might well be. Okay, so maybe if you have any other questions on this, otherwise I'm gonna move to the leptogenesis discussion. Okay, then I can mention a bit the leptogenesis part. This was one of the first questions that we got. And so it was clear from the beginning, I also mentioned it before, that you could not have thermal leptogenesis because it does not. So since you have an upper bound on the heavy mass at 10 to the 7 GeV, you definitely violate the Davidson-Ibarra bound. So you are too light to be thermal. there is the alternative of doing thermal leptogenesis with these NN star matrices in the Casasibara parameterization, but it's definitely not attractive and leads to large tuning or very large Higgs masses. So what we looked at was the resonant part together with Sergei Petkov and collaborators. And then later on, there was a paper that came out just last year of people that do a slightly different thing. So they tried a non-thermal leptogenesis, but assuming that the heating temperature to be below the Majorana mass. And in doing this, they introduce an extra fermionic dark matter and an inflaton, and basically you have the inflaton that decays into a neutrino. So it's a very different process. I'm not going to cover it here today because it's a bit of a different, more elaborate scenario, but you can go and check it out. So for the resonant part, the idea is that you can start off with a very minimal case in which you have only two right-handed neutrinos, so the lightest neutrino is going to be massless. The range is the one for the neutrino option. And to have resonant leptogenesis, you need to have that the mass splitting between the two right-handed neutrinos has to be of the same order of the decay width and significantly smaller than the average of their masses, so that you have some sort of amplification in the mixing, in the generation. So the question that we ask specifically is if there are any points for which you can have at the same time the correct baryon symmetry and the correct Higgs mass simultaneously. The question about the quartic coupling becomes really irrelevant here because it does not really play any game in interplay. So we already have essentially a constraint of neutrino masses and on the baryon symmetry, so this can be fixed a posteriori. So what leptogenesis gives you in this scenario is essentially another condition on the heavy mass that you want to see if it's consistent with the other one. So the first thing that we did was to use approximate solutions of the Boltzmann equations, and here you have the threshold correction to the Higgs mass. If you use the Casasibara parameterization, where you put these R matrices, that is arbitrary, the orthogonal one in between. And you have Y, that is the imaginary part of the angle, so the one that gives the CP violation. In this case, like the hyperbolic cosine of Y, and then like the mass of the neutrino to the cube. So we try to identify the range for the mass. And of course, to find the minimum allowed for the mass, it means that you need to, in order to comply with the Higgs constraint, you have to maximize the Y. And then in order to comply with the eta constraint, what we did was to maximize first the baryon symmetry over all the other parameters, all the mixing parameters in the equation, and then maximize Y as well at this point. And on the other end of the spectrum, if you want to maximize the mass of the heavy neutrino, you just have to set the the Y parameter to 0. And in this scenario, the situation was relatively easy because we realized that in this case, you basically have no constraint from the baryon symmetry. You can just play with all the other phases and you can always achieve the correct value of eta. So basically, this did not give any additional information with respect to the neutrino option. And the final window that was identified was actually pretty narrow. So the minimum turns out to be around 10 to the 6, again, with the Y that is between 2 and 3, depending on if it's a normal hierarchy or inverted hierarchy for the neutrinos. And this is, again, only the upper limit that came from the neutrino option assumption itself. And the delta M over M is roughly of the order of 10 to the minus 8, which is relatively small. So once we had these values, then we tried also to play a little bit with the full Boltzmann equations, but since the numerics is complicated, so we decided to fix points. So we took, for instance, the point at the minimum, so you have the minimum mass and the maximum Y, and then in this way, you could do basically a scan over the other parameters, and these are two panels of the 2D projections of the full scan that we did. And there are two panels that show the CP violating phase in the PMNS and the θ2-3 mixing angle. And these are the 1 and 2 sigma contours of compatibility with the baryon symmetry. And it was nice that kind of identified some preferred region. Of course, this depends on the specific values that we chose for the heavy Majorana mass and of the Y parameter. If you change that, things generally can move around, but at least it gave some sort of preference for the parameter space, so it doesn't all look the same. So for instance, if we went instead of the other end of the spectrum, so for the maximum mass that is allowed, setting Y to 0, at this point, this removes the CP violation from the R matrix, and you only remain with the standard model phases, so the delta and the Majoranas. And one thing that was fun to try is that even if you set also the Majorana phases to 0, you can still achieve the correct Majorana symmetry, varying only delta. So this is the correct Majorana symmetry that you want to match, and you see that it kind of really touches in one point. So there is also structure here then to reverse engineer this. This as an experimental concern is particularly hard, but it's good to know that you can also do this essentially.
So
with this,
what happens if you set delta to 0?
That's a good question, but I think you can achieve it with the Majorana phases. I mean, you have to turn on some other phase, and you can do it with the Majorana phases for sure.
Okay.
I will need to recheck again.
So your mass splitting in the heavy sector is very, very small. So the explanation of the hierarchy then is just from the Yukawas in your flavor choice for the Yukawas?
Yes, but it's not particularly tuned. I mean, yes, so the flavor structure comes purely from the Yukawa, but that's not particularly problematic because it's not really hierarchical. So it's not like you have to tune it particularly. You can do it with everything more or less at the same scale.
Thanks.
Yes, and there was also another group by Vedran Dar and his collaborators that also looked at this basically at the same time. We did analysis simultaneously. And okay, I'm not going to enter into this because this analysis is also very complicated, but they did something different. So what they did was to fix essentially the region where they explore the Z1 parameter, which is the equivalent of our Y, and then look for the maximization of delta M over M consistent with Majorana symmetry. And in the end of the day, the results are consistent. It's just that the parameter space is very complex. So depending on what you fix and what you vary, you might be testing very different hypotheses, and it's hard to find the logical overlap between things, but we definitely agree with the results. Okay, I'm going to stop here. Yes.
Yeah. Is there any way you could rule this out with low energy measurements?
That's $1 million question. No, I don't think so. Not right now, because what can you measure that rules this out? You have neutrino masses, they fit. You have the Majorana symmetry, which you don't really have one way it can be produced. You can have many ways it's produced. So it is possible to achieve it. And you essentially have no other signal because in the EFT kind of thinking, the next effect are dimension 6 suppressed by 10 to the 7 GV squared. So I don't know. I mean, if you have an idea of what could exclude it, let me know.
I mean, I was thinking mostly of, the neutrino parameters that you measure the low energy, but I don't think that at the end of the day, I think even if you add a third heavy neutrino, everything will be so degenerate that.
Yes. You could have another mass. I think it would just move things by a bit in some other region. But there's such a gap between the two things. So you can measure neutrino parameters, you can fit them, and then every consequence is in the thousands of dB. So you cannot probe it right now. And it doesn't leave any other signature.
Yeah. I guess another way of saying it is there's no prediction for the flavor structure and there's no prediction for delta.
No, there's no prediction. I mean, okay, yes, that's the correct statement. To me, it was also not obvious that it was allowed, like there was no contradiction.
Right. Yeah.
So yeah, you can go up to the point of saying there is no necessary contradiction, but there is also no prediction. The game starts becoming a bit more interesting or complicated once you want to accommodate other things, because this is a scenario where you're assuming absence of a lot of stuff. You're assuming that you have only the right-hand neutrino, nothing else that disturbs this, that you have no initial Higgs mass, and that's very hard to get. And I'm going to talk about this in a second, but it's really like if you want to add explanations for other sorts of physics like dark matter and so on, it is possible, but you need to add things, and then maybe it becomes a bit more predictive because the system gets more constrained.
Mm-hmm. Yeah, thanks.
Okay, so UV completions. This thing is clearly not UV complete. So the main thing that you want to explain is where does the Majorana mass come from as the only scale that you're assuming you start from. But at the same time, you have quite a good deal of constraints from the theory. So you need to have at least 2 eigenvalues in the Majorana mass, because otherwise you cannot reproduce the light neutrino mass splittings. You need to avoid that the Higgs mass receives other large contributions, which means you don't have anything that generates this interaction here, if you want to think it again in EFT moved up. And this is relatively hard to avoid. And you want to have that the electroweak vacuum stays stable up to scales, say at least up to the Planck scale. And you don't want to spoil the running. So if you have extra BSM states, if they're not heavy enough, they could spoil the running. So all the conditions that you have set could go another way just because you have a different running lower scale. And then of course you want to avoid fine tunings because that's kind of the game that we were playing. So the last one is probably the hardest part to maintain. So there are a few options that have been explored so far in the literature. By far, the most explored was the conformal UV completion. So there was a paper by Manfred Lindner already 3 years ago. And then some of his postdocs continued to study some aspects of this model with some modifications. And there was also another paper last year that, to be honest, I still have to read carefully. I'm not sure if I completely understand it, but this is the one that connects to gravity. So this is a paper where they do the full combination of adding gravity, inflation, and having a subsequent mechanism that generates scales. And eventually it kind of plugs on the first model that I'm going to talk about, where you have a Gilner-Weinberg mechanism and then goes down to the electroweak symmetry breaking via the Neutrino option. So this is basically kind of a UV completion of the first one in a way. And then we had a paper where we briefly explored the perturbative generation from the Planck scale. And there was also a paper by Jim exploring potential string theory UV completions, but these are really not touched upon because I really cannot comment on it.
What is the perturbative generation from Planck scale?
You cannot. So this is an X because it was actually a no-go way. So the idea was this one. Which is just we realized playing the number games that if you want to have the PV, so the 10 to the 7 GV for the Majorana scale, that is roughly 1 loop correction away from MGAT or M Planck for the values of the Yukawa couplings that we have. So we know that we want a mass at 10 to the 7 and that we have Yukawas over the 10 to the -4. If you plug in a loop correction and you want to guess what scale you came from, it's either GAT or M Planck. So that looked like a fun accident. And we checked if it's possible to have it. So that you have some sort of generation from the Planck scale of Majorana scales that typically would become like some sort of democratic matrix. So like if you have some sort of gravity condensation that creates Majorana masses for neutrinos, it doesn't distinguish the flavor, so it's democratic. So typically it has 1 more eigenvalue. You can, there's 1 eigenvalue, you can add 1 more with perturbation.
Maybe I missed something. So the Majorana mass for neutrinos it breaks lepton number by 2 units. So you're assuming that somehow broken at the Planck scale and mediated through what? Through loops?
And mediated through loops, but it doesn't work. Like the message of the paper that it doesn't work.
Yeah.
Yes, find somehow a way.
Here.
Yes, so that you can start off with some sort of condensate, and then via loops somehow get it down to the PEV. And via loops means either you start from 0 and you have a relative correction that generates something non-zero on top of it, or having something large and then by RG running, bringing it down to a smaller value. But I can cut the story short. None of these work, essentially. I can even skip that part and get down to here, which is the right point. The first one doesn't work because you have the symmetries to break. So there are symmetries that if you break them, you end up basically violating the Higgs constraint. So specifically, when you have the Majorana mass that has one eigenvalue, you have a U2 symmetry here and a Z2 for the third. And then if you want to protect the Higgs mass from this big eigenvalue that you have at the beginning, then you have basically to shut down the corresponding column in the Yukawa coupling where this neutrino talks to the Higgs. But then, so if you shut it down completely, then this scale remains isolated and you don't generate anything anymore. So you don't generate other Majorana masses, you don't generate neutrino masses, you don't generate anything. And if you break it just by a little bit, the Higgs mass explodes immediately because so the little bit has to be smaller than 10 to the minus 14, essentially, which looked like a tuning that was a bit too much.
I'm a little confused. Are you trying to do something that you can't do in, say, SO10? In SO10, you would generate the masses of the right-handed neutrinos.
Probably yes, but then you have extra degrees of freedom. We didn't really try to embed this into a larger representation.
But that's
maybe we can look at it.
I mean, in the matter sector, you have the same numbers of degrees of freedom. You're just putting everything into a 16 of SO10. And, you know, if you have everything else is the gauge sector, and then you need a Higgs sector to break SO10 down to the standard model.
But don't you fall on the same problem of like, so like if you have a symmetry that protects, so somehow
you generate the right-handed neutrino masses. I mean, there's several different ways of doing it depending on the choice of Higgs representations that you choose.
Yeah, but you'll have to sequester the top loops because then you'll have top loops contributing to the Higgs mass. So that's what you have to show, right? If you're going to do it like that way. Right, because you're assuming some kind of symmetry in the UV, which prevents top loops and all the other fermions from contributing quadratic divergences to the Higgs mass, and you're only relying on the quadratic divergence coming from the Higgs sector.
Yes, so it's always the same problem. Either the Higgs talks to the heavy particles, or it doesn't, and then it's hard to do it something.
No, so you can do something like Keith is suggesting, but then you have to then also shut off, you know, quadratic divergences from all the other fermions because you're only looking at the quadratic divergence coming from the neutrino sector, you see.
Yeah, but Tony, I mean, protecting the Higgs quartic coupling, the standard model Higgs quartic coupling, is not a big problem in SO10 either, right? Because you have the additional scalars that you can use to do that.
Yeah, I was more worried about the mass squared to the Higgs. You could have the top could contribute to that.
Of course, yeah. Well, if there is a new sector at the GOT scale, you have to really explain why it's not feeding into the Higgs mass at the loop level, right?
Yes. You just multiply this by a multiplet, and then you can have a more complicated system of who talks to who. But
yes. So how are you sequestering the neutrino sector from So you're saying that you're introducing a UV completion which only talks to the neutrino sector and nothing else?
Yes, which is also another
No,
assumption.
I'm just trying to understand. Yeah, no, I'm just trying to understand just the philosophy.
Yes, no, we
Is
were
that
looking
right?
into the neutrino specifically, and so the idea, so okay, because the idea was born from the numerical coincidence of saying, okay, the mass that we want, which is the Majorana mass, is one loop away from MGAT or M Planck. And we don't really want to start playing with adding extra fields because then we need to reconsider everything. And let's see how far we can get with just these. Then we only focus on having the neutrino masses. And you can have, in principle, speculatively, a Majorana masses generated by gravity condensation. So if you could take the mass generated very heavy and then run it down, so had the loop effect there, so that you bring down to the PEV, and then from the PEV start with the Neutrino option, that it would work. The problem is that you cannot have an easy one loop connection, but not even two loop connections without adding extra fields because of the symmetries, because you have to break the lepton number twice, and this is not possible at one loop. Nothing does it. At two loops, you have too much suppression, so everything goes to the wrong values. And with any other attempt, you end up having basically a too close connection between the heavy sector and the Higgs, because you have nothing in between that can mediate. So you have a symmetry that is either open or shut, and you have the only way you can move on is you open it by 10 to the minus 15. And maybe you can do this with a chain of things. We didn't really explore that.
But it sounds like you're arguing that it's much easier to do it in an SO10 gut or something similar.
I'm not an expert in SO10 gut. I have no idea. It might be like if you had layers, but then you have to be careful with understanding if these other states are also going to contribute to the Higgs or spoil the running, or
But
like,
I mean, this
has
has been well studied, right? I mean, you have an intermediate scale, you have a breaking down to some intermediate scale. So you intermediate gauge group, and then that gauge group breaks down to the standard model.
And I will look into it. Yeah, it can be.
And yeah, you can do it either without supersymmetry or with supersymmetry, and either way it works.
But I would say that this idea is incompatible with guts, because guts treat the right-handed neutrino the same as the top quark, right? Because they're all in the same representation. So I think this neutrino option requires you to treat the neutrino sector as something special and sequestered from all the other fermions. That seems to be.
That's what I'm saying, is that if you find that doing it this way is difficult, it sort of points you back towards a simpler version where you are sticking the right-handed neutrino in a single multiplet.
I see. Yeah.
I mean, you might even.
Or perhaps no. I would say that you would probably don't consider SO10, consider SU5, and treat the singlet as a singlet, as not being part of a bigger multiplet. But
well, you could do that as well.
You can isolate the neutrino sector if you like, and only somehow connect that to the Higgs. But that's also
right. But then you're putting in the right-handed neutrino masses more in by hand, which you
probably
can do.
Yeah. Yeah, I don't know. Yeah.
Right. I mean, that would be the standard way of doing it in SU5, right? Or you can go to flipped SU5, and then it's again, then the right-handed neutrino is in the 10.
Ah, yeah, right. Yeah.
Okay, no, I should let you
go.
All
right, I can show you. Sorry.
Yeah, sorry. Yeah.
I can show you a model that more or less works, even though it still has some sort of tuning.
Can I just ask a question before you move on?
Yes.
So the numerical coincidence, is it unrelated to the fact that you get typical M Planck for type 1 seesaw with order 1 Yukawas? Or is it the same numerical coincidence?
Is it?
Right, because you're adjusting the correct neutrino masses, and you just so happen that you got the Yukawa of 10 to minus 4, 10 to minus 5 for the scale that you're preferring. But isn't that product just the same numerical coincidence that the type 1 seesaw gives you, right?
I mean, in a way, it has to be, in a sense that you have a product of two quantities and that's constant, right? So I can split it into parts, but then...
So it's not a new coincidence. It's the same statement of the type 1 seesaw, right?
It probably in the end it is, because you still have the same functional dependence. It's always Yukawa squared times m.
Right.
So
right.
you can write it into separate factors, but then in the end it has to work out with the same numerics. No, yes, it probably has to. Yes, that makes sense.
Thanks.
All right, so one model that more or less works goes in a bit of a different direction. So it tries to build on the conformal aspect. So again, disclaimer, this is not my work, so I can tell you what I understood, but I might not be able to answer all the details. So the idea was that they look into conformal completion, and what they find is that the minimum extension that you need to have on top of the neutrinos, or the type 1 seesaw, is to have two extra scalars. So these are the S and the R. And then you have the one of the two has one sign, so one flip symmetry, so it only has quadratic couplings. And the other one needs to have a Gildener-Weinberg point, so basically a point where its quartic coupling lambda s runs and it crosses 0, and if that happens at that point, basically it triggers a spontaneous breaking of. So this takes a VEV ds, while the R remains VEV-less and the Higgs as well, at least for a while. And then the running continues. You can have the Neutrino Option mechanism, and that you can have electric symmetry breaking. And the scalar degree of freedom that you get out of the S parameter is the scalon. So the VEV that you take is going to be this Vs, and you have pseudo-Boston bosons that are very heavy. You can assume that you don't see them because they decouple as well, and they don't really have any impact on the RGE. They don't disturb this thing in a particular way. And the Majorana mass, in the end of the day, scales like the VEV of this scalon times its own kind of Yukawa coupling, this Ym that is here. So they find that everything works and it has some nice properties. The thing is that you need to have restrictions because, of course, you're writing scalars. So the hierarchy kind of still pops out, and you need to forbid the scalars from talking too much with each other. Otherwise, all the VEVs tend to uniform. So this mechanism basically works if you have that the coupling of the Higgs to the scalar that takes a VEV is very much suppressed. And I think this was, again, 10 to the minus 14 or something. I could check again the paper, but a very small number. And also the coupling to the R scalar is suppressed in a way that basically prevents it from spoiling neutrino masses. And there are also other constraints in the parameter space. The thing that I find is that there are the regions of the parameter space within these theory constraints where you can have that you match the scalar potential, you match the neutrino masses, and there are no Landau poles as a theory consistency check. And in a subsequent paper where they continue to analyze this, they also found that if you check it more closely, you can also have some first order phase transition in a region of the parameter space of the one where the Neutrino option is valid. So this is one example of something that could be tested because it does generate gravitational waves. These are two benchmark points with a frequency and the omega. When you see that they can cross like an actually measurable region, then again, it's not really predictive. There's a bunch of benchmark points that can allow for visible signals. And it's not a direct consequence of an option, but of the specific completion, but still it's kind of interesting because it's the one other handle that we have on top of these. Always people of the same group try to modify a bit this model at some point, trying to see if you could extend it with dark matter as well. And they had this paper here last year. So basically it's the same sort of construction, but instead of the Gildener-Weinberg, in order to have that this scalon takes a VEV, they have a new strong interacting sector with fermions that condense. So you don't need two scalars at this point to have the running game to play. You just need to have this thing that condenses, and you still get the VEV, which has to take the same value for everything that work out. But what you gain is that you have a dark matter candidate, which are the Goldstone bosons of the global chiral symmetry that is broken by the condensation. So like the pions essentially of these. Again, this model still has the tuning of before. So the coupling of lambda that talks to the scalar has to be smaller than mh squared over the new VEV squared, which ends up being 10 to the minus 12 times this quantity that could be order 1. But so this is the kind of number that always pops out, 10 to the minus 12, 10 to the minus 14. So some sort of tuning is always there. I don't know if you could really forbid it, but that's a constraint that stays. And these are the range of masses that they found for the dark matter. For instance, you have to multiply by, so the VS ends up being 10 to the 10. So you have this thing that takes a VEV at 10 to the 10 GeV, and then the neutrino mass is 50 PeV. So they're only like 2 orders of magnitude far from each other. And you can have the correct relic abundance for the dark matter candidate via freezing, and it will have a mass. Now I would have to multiply the numbers, but I think of order of the hundreds of thousands of GeV. No, sorry, this is going to be very heavy. This is 10 to the 8 GeV. Yes, and this I think is my very last slide. There are also more papers that I mentioned before that covered models. There's also this other extension by Linden et al. Where they had gravity, and they see that inflation can work in a two-step process, but you still need to have some sort of tuning in the scalar part for the UV completion. All right, so this is just my summary, wrapping up again this thing. So the only predictor thing that Neutrino option gives you is the range for the mass and the Yukawas. And then if you have nothing else, you need to have a bare quartic clumping that has to stay there. It does not solve the hierarchy problem by itself, but it's an interesting new approach because you take this problem to another scale and you have it generated in a way that is different from the usual techniques. And it has this interesting feature that you basically have a combination of the fact that you have fermions with the fact that you have one parameter that breaks at the same time, the lepton number and the scale, and that the RGE rightly has this form where lambda runs to lower and lower values, and these all kind of conspires in order to make this thing possible. There are no BSM signatures predicted, as I was saying before, which is a blessing and a curse, because of course it's not excluded, but it's also not confirmed. I mentioned resonance leptogenesis as a baseline scenario that is consistent with the pure neutrino option with nothing else. But if you add other things like inflatons, dark matter candidates, and so on, you can have also other kinds of non-thermal production, and discuss a bit the UV completion. So I think I'm done. If you have more questions, I'd be happy to answer. Thanks.
Thanks. Let's thank the speaker, Ilaria. Any questions from the audience?
I'm just curious why you call it UV, this attempts UV completion. Like, if I just approach your model, it's all consists of like dimension 3, dimension 4 operators, you know, like in the most naive sense, it is UV complete, no?
I mean, yes. So for me, if you just write it by hand, like the standard model, it stays there, right?
Yeah,
it doesn't self-destroy.
I mean, like it's still a renormalizable theory, nothing wrong with it. You know, it's more like, I don't know, embedding, I would say, right, rather than completion, right? So what you try to do is to have some embedding with some new scales built in, like M Planck or M GOT or something like
yeah,
that. So I would call it attempts at embedding, right,
okay,
rather than completion, because theory is renormalizable, right?
No, I agree. Yes, I mean, yes. So to me, the question is still answering if you add something else how is this stable,
Okay.
which is the same thing that you asked to the Higgs, right? It's the hierarchy problem. So,
Yeah.
but I agree, yes.
Because if you talk to someone like Misha Shaposhnikov, you will say, "All right, this is all good. There are no higher scales, right? There is no sensitivity. That's your highest scale. Fine, everything is consistent, right?" So
I would be happy
that's
with
of
it.
course a very debatable point. But
Yes.
what it looks like to me like you're doing is like attempts at embedding, not completing, right?
Yes.
Okay,
Yes.
it's not important.
So this model then, if I compare it with SUSY or composite Higgs, right? You started out saying that these models are all complex and tuned, but at the end of the day, your attempt at this embedding as well, right?
Yes.
Is also complex, and it's actually more tuned than say SUSY or a composite Higgs model.
Yes, that's a
would
very
that be
fair
a fair
point.
assessment?
No, that's a fair point, but it's a property of the UV completion, not of the option itself.
Yeah. No, I mean,
there
I
is a big
understand that you're
difference.
exploring a different idea.
No, but I agree. I agree.
And that's
Tony, there
fine.
is a big difference with SUSY, right? Because here the loops are not compensated, right? There is like, you know, if I do the most naive thing, I write a loop, and you know, chop it off at lambda UV or something like that. In this all these models, you get lambda UV sensitivity, right? So you would say, all right, this is a very inelegant way. I would revert to dimensional regularization, and only the real thresholds will appear, right?
Right, exactly.
Which in SUSY you don't have that problem at all, right? You can even cut things.
That's
you
right.
cut it in supersymmetric way. There is nothing would appear, right? So
no, but you supersymmetry is not elegant because of a huge number of the adjustable parameters, right? Free parameters, over 100.
True.
Even in standard model, there are a couple of, almost couple of, with neutrino masses, couple of dozens of adjustable parameters, but okay. But I don't know.
You don't have quadratic sensitivity to high scales. That's the advantage of it, right? So
you gain one thing, right? This Higgs mass loses m squared sensitivity.
That's correct.
But then you acquire 80 new free parameters and looks ugly. In this sense,
Misha, you don't really. That's a little bit of an exaggeration because you have to, most of these parameters are supersymmetry breaking parameters, and the way you break, but the way you break supersymmetry gives you almost any way that anybody's ever talked about how you break supersymmetry gives you relationships between these parameters. So they're not all independent.
But we are not sure that any of this method of breaking supersymmetry is correct. Now there is no hint from.
We don't know that supersymmetry is correct. We don't know anything is correct beyond the
that's why I'm saying. I take the worst case scenario: 106 parameters in supersymmetry with including the breaking parameters. With the standard model, at least you can say, okay, 20 parameters. Still a lot, but if you assume there is no naturalness, there's fine-tuning somewhere, I don't know, high intellect or whatever, takes care of this fine-tuning in the UV, then, okay, 20 parameters is bad enough, but you still can live with that almost happily. Not quite happily, I understand you, because happily you would live if in the standard model there are no quadratic divergences. Then you can live more or less happily, right? But it's not up to decide, not up to us to decide after all. I'm not, you should not, and I want to confirm to the speaker, I'm not against any new attempts to do that at all. I would be happy. In fact, I'm waiting for many years already. Somebody comes and tells, look, guys, you are all doing wrong things, and I know how to do the right thing. And look how nice it is and simple. But so far, okay, there are many attempts. Some of them are better, some are more uglier, but not this one which will make you happy, right?
Yeah, I agree personally. and I have to say that this idea in particular is very, I don't know, like green. Like it's not. I also don't think it's fully developed. Maybe the seesaw is the wrong model to try it out. Maybe I should try it out with something else, with some other fermion model, or something different.
Yeah, we all, strive. I think I can say all of us, we strive for deeper understanding and
Yes.
for simplicity. But our what we request is probably too much. Not only we want simplicity, but we want to understand all these parameters in the standard model. We want to build fully consistent UV completion, which is simple, or at least half of the completion, right? So maybe time is not ripe yet. Who knows? I don't know. I'm an old-fashioned person,
Well, I like simplicity as well. Like, I also don't like too many parameters, too many fields, or too many things. But if it is like this, what can you do?
No, but on the other hand, sometimes for the sake of happiness of the humankind, you should do this, but not too often. Like you probably all know the story of Pauli, who invented Young-Mills theory before Young and Mills for about 6-8 months earlier, but he never sent it to any journal, only wrote in a letter to Pice. And this letter exists now, it was published. And you see, he moved from this Kaluza-Klein side, compactified 6-dimensional space onto 4-dimensional space and the sphere. And he got the full SU2 Young-Mills theory. And then several years later, people asked him, whilst he's alive, and people asked him, after Young and Mills published, people asked him, why didn't he not publish this? And then he answered, in 1932, I predicted the massless neutrino, which was not known at that time. Okay, and then it is still not discovered. It was discovered after his death, right? After Pauli's death. And now in this theory, I see 3 massless particles, which we don't see in nature. And I just didn't want to multiply the set of massless ghosty particles, which nobody sees in nature. I didn't want that, but he was not right, okay?
Yes, it's true. It's true.
Yeah. Okay, I'm sorry for interrupting. I thank you for the talk. It's very.
And thanks to you for the comments. They're really useful. It's good to stimulate the discussion. I'm happy about that.
Okay.
Any more questions from the audience?
Have you thought of the fermion as being something different, other than a right-handed neutrino?
Yes,
right? Like
not seriously. I have not tried anything out yet. Like what? Like matter can't.
Yeah, I cannot think of it. You could say, oh, maybe you can pick the problem of dark matter, but I don't think you can have something.
I mean, the thing is that it has to
heavy.
be, you have the anomaly constraints. Whenever you're at the fermion, it's not like you could be anything. So the right-handed neutrino fits in with all the possible constraints. You know already that the 3-level matching gives you the neutrino masses, so that's already properly taken care of. So you will need something that is well motivated
Sure.
from some model that already works out from other points of view. No, maybe it could be like a type 3 seesaw, for instance. Like you could have a triplet, you have more fermions, so you have a bigger loop somehow. You can change the way it works out. Qualitatively, it's going to stay the same, I think. Maybe you have more signatures from the chart ones.
Yeah. I think the type 3 is just difficult for charge lepton violation, I think.
Mm.
It's very strongly constrained, but maybe.
Mm. All right, if it's very heavy, maybe you
Yeah,
can.
maybe it's okay.
Any more questions? If not, let's thank Ilaria again.
Thanks to you again.
Yeah, thank you, Ilaria.
Thank you very much. Thank you for